When I was a child I liked video games, but even more so I was fascinated how they work. And in this series we continue that tradition by studying how video games save and load their progress using passwords. Metroid is an insanely successful Nintendo brand that was made even more popular when they made the Game Boy Advance remake, which introduced the very cosplayable form of the titular character. But the game was initially released on the Nintendo Entertainment System and was simply titled Metroid. This game was initially going to have a battery-packed save and load feature similar to its Japanese Famicom Disk System counterpart, but at some point in the development they forewent this choice, probably to make the game cartridges cheaper, and they produced a password save feature instead. What makes this password screen particularly memorable, besides the strange lowercase font, are two things. First, it has the full English alphabet, meaning that contrary to the later guidelines from Nintendo themselves, it is actually possible to input obscene words in this one. Secondly, the password is long. 24 characters at 6 bits per symbol brings the password length to 144 bits or 18 bytes. For comparison, here is the apparent password complexities in games we have previously featured in this series. The least complex of them has been Bubble Bobble, where you can only possibly try and input 100,000 different passwords before you have exhausted them all. And the most complex has been Swords and Serpents, where if you had billion trillion people typing a billion trillion different sets of input a billion trillion times in a second on a billion trillion different planets in a billion trillion different universes, it would still take about 3,000 quadrillion years before all possibilities would have been covered. Most of the passwords have been less than 144 bits long, so where does Metroid need all this storage? Let's have a look at the Metroid world. This is Planet Zebus, where Metroid is set. In Planet Zebus there is an extensive tunnel system. This map consists of 32 by 32 screens, some of which are separated by airlock-type doors. Most of these airlocks are free to open from either side, but some of them requires blasting them several times with missiles. Throughout the map there are also plenty of collectible items such as weapon upgrades and health tanks. With such a huge map, you can imagine there are quite a few of these, and the game remembers your interactions with all of them. In fact, let's dive straight into the password contents without further ado. This is my password encoder and decoder that I wrote in C++. I used the user literals operators to help make the code easier to read. The password is 144 bits long as previously discussed, or 18 bytes. The following list will be grouped topically, not by bit position, so the bit positions may appear to jump from place to place. A checksum and an encryption key are stored in the last 2 bytes, 8 bits each. More about these later. That leaves exactly 16 bytes for everything else. There are 8 equipment bits which are saved in the 9th byte. Each of these equipment bits is, well, 1 bit. There is a 9th bit that indicates if Samus is running around in a leotard, a special mode that is unlocked by previously having beaten the game in an exceptionally short time. 5 of these equipment bits are seemingly duplicated in the password, but they are not actually duplicates. These 5 separate bits indicate whether the power-up has been picked up, not whether Samus has it. It is possible to create a password in which this item is removed from the game without Samus ever acquiring it. 19 missile doors as discussed earlier, 21 missile power-up bits, 8 energy tank pickup spots. Now we get into the enemies and bosses. First, 1 bit for each of the 5 Sabotites. These are the glass-fused things in the Mother Brain room that regenerate if you don't destroy them quickly enough. 1 bit for the Mother Brain, also in the Mother Brain room. Then there are 2 sub-bosses, Ridley and Clyde. The state of each boss is indicated in 2 bits. A value greater than 0 indicates that the boss is dead, and a value greater than 1 indicates that the player has activated the statue corresponding to the boss in the statue room. The number of missiles that Samus has is saved as an 8-bit number. The maximum missile count is not saved separately. It is calculated from the number of missile acquisition bits times 5 plus the number of beaten sub-bosses times 75 for a maximum of 255. Note that it is possible for Samus to have more missiles than her maximum number. Next comes the age. The game keeps track of how long you have been playing. This timer ticks once per 256 frames, which means about 17 seconds per 4 ticks. However, this number has a peculiar format. It is stored as a 32-bit integer, but the lowest order byte of it counts from 0 to 207, not 0 to 255. This timer is used by the game for deciding which ending you are eligible for. The timer code is exactly the same for the NTSC and PAL versions of the game, even though NTSC counts 60 frames per second and the PAL clocks 50 frames per second. This means that on the North American and Japanese consoles you have to beat the game in under 59 minutes to get the best ending, but the rest of the world can take almost 71 minutes to qualify. It is funny that they chose a 4-byte integer for the time. It might not sound like much, but this is so much capacity that it takes almost 500 years for the counter to wrap and almost 2 years of non-stop playing even to get the 4th byte to advance by 1. It is no wonder that Kent Hansen, aka Snowbro, whose excellent disassembly I referred to extensively while making this video, thought that this byte is unused by the game. Anyway, moving on our list, next up is the area code. The area code is 4 bits, 5 bits or 6 bits, depending how you look at it. 6 bits are stored by the game, but all the major decisions are made from the 4 lowest bits and sometimes the 5th bit as well. I call the 5th bit an extension code to the area. There are 5 areas in the game. Let's review this variable in more depth later. Besides the 6th bit of the area that the game does not use for any purpose, the password contains 10 other bits that do not influence the game in any manner. I call these bits ghost bits because they are totally ignored by the game. There's just room for them in the password, but they are not saved in the game's RAM, and new passwords generated by the game always have these bits 0. Finally, my structure has 2 special flags here, but these are just internal parts of the password codec, not part of the password encoder. Now let's move on to the encryption and decryption. There are 3 steps to the password encryption. Calculate the sum of the first 17 bytes and store it in the 18th byte. Rotate the first 16 bytes right by the number of bits indicated by the 17th byte. And convert the result into 6-bit characters in a manner very similar to base64 encoding. Conversely, the decryption repeats the same steps in reverse. Convert the 6-bit characters into bytes in a manner resembling base64 decoding. Rotate the first 16 bytes left by the number of bits indicated by the 17th byte. And verify that the sum of the first 17 bytes matches the 18th byte. Yes, this is one of the few games where password encryption does not involve the XOR operator. In my design I would have preferred to handle the password as a single 144-bit integer, but alas, there is no such data type in standard C. The biggest that GCC has is 128-bit wide, but there would be no particular advantage on choosing such a compiler-specific type over a standard-compliant 64-bit type. So I represent the password as an array of 64-bit integers. The outermost operation is to convert between 8-bit and 6-bit representations of the password. Here is how the conversion works. First, the symbols correspond to some particular numbers in range 0 to 63. Then groups of 4 characters are packed into 3 bytes as indicated by the diagram. In encoding, this just means pushing 6 bits in from the right side. In decoding, I pop the same 6 bits out from the left side. To convert numbers into characters, I just index the string, and the opposite operation, character into number, is managed by the find method of the string view. Actually, that's wrong. I missed one symbol again. Yes, the password character set is indeed 64 symbols long, but there is one more symbol. There are 4 different kinds of spaces. First, of course, the password is grouped in 4 groups of 6 symbols each, and there is a mandatory space between each group. Okay, that's cheating. That's not really a space. But if you press the B button, you can skip over some slot and leave it empty. This is kind of inconvenient since you can only skip backwards, not forwards. In any case, this is a valid password. It gives you the leotard, 4 health tanks, 5 missile packs, and kills 3 Zibatites and the mother brain. The slots that you skip over are actually zeros, and you can just input a 0 instead. This is the same password essentially. However, if you navigate to the bottom right corner and press A to actually input a space, the password is no longer valid. And that's because this is a different kind of space now. Yes, that is a valid symbol too. This is a valid password that contains the second kind of space. Replacing this space with 0 will not work, but I can replace it with a dash. This space has the number value of 63, like the dash symbol, not a 0. However, in this password, which is also valid, neither 0 nor dash works as a replacement for the space. This is a third and yet different kind of space with a numeric value of 255. It leaks into the next character. I have to adjust an innocent neighboring letter too. And now it validates and produces identical result compared to before. Here is the updated chart. The space has 3 different values as indicated. When the value is 255, the 2 extra bits overlap with the preceding character and are ORed together as indicated by the red arrows. And this has to be accounted for in the password decoder, of course. I do not account for skipped slots because it is difficult to think how to write them other than as verbatim zeros. The next operation is to rotate the password, left when decoding and right when encoding. The number of bits to shift is indicated in byte 16, which is stored near the top of the third 64-bit integer. Next is the checksum calculation. The first 17 bytes are added together and this result must match the 18th byte. When encoding, the result is placed in that byte, and when decoding, these 2 values are compared. This is my checksum function. It basically just creates a byte pointer into the data and calls std_accumulate on it with a plus operator. Everything else in it is just metaprogramming to give a compile time error in non-portable use cases. If we check out the compiler explorer, pretty much all compilers generate quite tight CMIT code for this function, except the Microsoft product, which kinda goes meh, who cares, producing a 16 iteration loop instead. Let's have a closer look at the CMIT code. First, it loads all 16 bytes from the memory address into XMM0, a 128-bit register. Then it creates a copy of that register, XMM1, where the bottom half contains a copy of the top half. GCC uses a shift instruction for this purpose, while Clang uses a shuffle instruction. I am not sure if there was any difference in performance. Next, these 2 registers are added byte-wise and the result is stored in XMM0. At this point, the low 64 bits of XMM0 contains the pairwise sums of the high and low bytes. Next, it initializes XMM1 with 0 in preparation to the next step. Then it calls an operation called vp_subv. This little used instruction does the following. First, it subtracts all bytes in the first operand from the corresponding bytes in the second operand. This produces 16 new bytes from the 2 sets of 16 bytes. Then the low 8 bytes are added together and stored in the first 16 bits of the lower half of the target register, and the same is done for the upper half. Finally, the vp_extrb instruction is used to fetch the lowest order byte from this register and store it in EAX, the function return value register. Here the vmoved instruction chosen by ICC would have been shorter, but in terms of operation and outcome, vp_extrb is kind of cleaner, I guess. And this is how it calculates the sum of 16 bytes in just 6 CPU instructions. ICC does an additional movsx here, but that instruction is redundant in this context because the function returns an 8-bit value and the rest of the bits in the register are irrelevant. Note that this is not what these compilers originally did. GCC 9 and Clang 8 both compile this function into a longer sequence, but I filed in both compilers' bug reports that were well received and the code generators were changed. Once all the checksum stuff has been done, it is time to access the actual data inside the password. First though, I will do a byte swap for the data, because the left-aligned byte indexes in my design are a bit cumbersome to work with. Here is how the byte swap operation is performed. If we use the compiler explorer and inspect how 4 popular compilers compile this function, we can see that GCC and Clang both optimize it literally into a single CPU instruction, while the 2 corporation-made compilers kinda do their own thing. When encoding, the data is placed in the password using a bit shift and the bitwise OR, and when extracting, the data is taken from the password using a bit shift and the bitwise AND. The C++70 structured binding declaration proves very useful here, making the code simultaneously very compact and expressive. Oh yeah, did you know that this game has a special password? That's right, if you enter this password, not a password 00000-Bisqwit, you will get a secret game mode. This game mode starts like the normal game, but on every frame, that is 50 or 60 times in a second, 3 things will happen. Samus is given all power-ups. She is given 5 missiles. Her health 10th digit is set to 3. And you can see how it works. My default weapon is now the Ice Beam, and I have an infinite supply of missiles, and Samus can take any amount of hits from enemies, but the health will never go below 30. Actually, you only need to enter these 11 letters. The mode is activated by any password that begins with those 11 letters followed by 5 blanks or zeros. Whatever comes after those 16 symbols is irrelevant. This password skips all the checksum logic as well as the encryption and decryption, and in my program I reproduced this behavior. That's what the magic words array is for. This is the only hard-coded password in the game. There is some debate on what the nar in the nar password refers to. Rather than parrot fan theories, I will just refer and urge anyone to check out the Metroid fandom wiki for this article if you are interested. Now let's have a closer look at some interesting details in the real passwords. There are 8 energy tanks that are separately saved in the password. However, Samus can only have up to 6 spare energy tanks. If you collect more than 6, the game just discards the rest. The password has a bit for the mother brain. However, the game will actually never give you a password in which this bit is set. If you die in the game after the mother brain is killed, the game deliberately punishes you by giving you a password in which not only the mother brain is still alive, but so are the 5 Zebatites and the 2 missile doors leading there. For the 2 bosses, Ridley and Clyde, the password saves a 2-bit value for both. A non-zero value means that the boss is dead, and a value greater than 1 means that the statue corresponding to the boss has been lifted. The value 3 is unused by the game, but it is interpreted to mean the same as 2. If you encounter a password in which the value is 3, it is definitely crafted manually. There are 10 unused bits in the password. These bits are not saved by the game anywhere, and they are always 0 in passwords generated by the game. This means 2 things. If you encounter a password in which one of these values is non-zero, it is a manually crafted password. And for every valid game state, there are 262,144 different passwords that represent the same state. There is one more unused bit right here. This is the 6th bit of the area code. The game will never set this bit, but if you manually craft a password in which this bit is set, the game will remember it, at least until the next elevator where it is reset. Nevertheless, the value of this bit does not affect the game in any way. The seed is an 8-bit integer that is used for rotating the password bits. The seed also contributes to the checksum calculation. There are 256 possible values for this byte. However, because the data area that it shifts is only 128 bits wide, the first 128 values accomplish exactly the same outcome as the second set of 128 values. Moreover, the game has a condition that it will never generate a password where the seed is divisible by 16. I'm not sure why. I mean, I know that the shift that is divisible by 8 means that the bytes are just shuffled around, but the password operates on 6-bit symbols, not 8-bit bytes. I digress. In any case, if you come across a password where the seed is divisible by 16, that password is definitely man-made and not generated by the game. Now the area code. The area code is a 6-bit value that has 4 significant bits, 1 bit that indicates something that I am not sure what it means, and 1 bit that is completely unused. Let's study the 4 significant bits. This value, which ranges from 0 to 15, has 5 valid values. Values 0 to 4 correspond to the 5 game locations: Brinstar, Norfair, Craig's hideout, Turian, and Ridley's hideout respectively. But what happens if you enter a value that is outside this range? To find out, let's study what the game does with this number. Let's make a table. Let's just search for references to this variable in area. Here's the first one. The scrolling direction is vertical if the area code is non-zero and horizontal if 0. There was one similar bit of code somewhere that sets Samus's starting coordinates, but I couldn't find it again when I was making this footage, so I will just add it here. Here is the next one. The ROM bank number is set using a table. This table contains 5 values, 2, 3, 5, 4 and 6. If the number is 5 or greater, the code will access data that immediately follows this table, which is this routine over here. The exact values are shown on the screen. This value is saved into the switch pending variable. The code that reads the switch pending variable subtracts 1 from the value and writes this to the MMC1 mapper. If we look at the MMC1 documentation for that register, we see the low 4 bits of this value are used to select the ROM bank and the 5th bit is used to enable or disable the program RAM. However, it also says that the 5th bit is ignored on MMC1A, and this game is MMC1A, so we only need to care about the 4 lowest bits. Additionally, because this game only contains 8 banks of code, not 16, I think it will discard the 4th bit and only care about the lowest 3. After the ROM bank has been switched, the next part is that the full 8-bit byte minus 1 is multiplied by 2 and the resulting value is used as an index to this jump table below. The first 5 values map nicely into jump pointers, but after that things go very wrong. It loads pointers from code that is not meant to be interpreted as data. This is the table of jump addresses. The first 5 are normal. Value 10 loads a pointer to a memory region that begins with byte 2. This is an illegal CPU instruction that kills the CPU. Literally. When the CPU executes this instruction, it goes into an infinite loop where nothing can wake it except a console reset. Values 5 and 6 point to the console's internal RAM. This is the cache of the OEM where sprites are stored. At this point, the memory contains nothing but FOFO values, which is a branch if equal instruction. At this point, the 0 flag is not set, so no branch will happen, and the next instruction is executed. This instruction too is FOFO. This process will repeat 48 times until it hits memory address 300, which contains the following instruction BRK. BRK activates a software interrupt, and the interrupt vector in Metroid happens to point to the reset vector. So area codes 5 and 6 will unconditionally reset the console. Area code 7 loads a pointer to EFO. This is a mirrored copy of 6FO, which is part of the CPU's RAM. This portion of the RAM is unused by the game and is 0 initialized on reset, so it will also trigger the interrupt, which leads to an unconditional reset. Area codes 8, 12 and 15 load pointers to valid program code within the game, albeit in totally wrong contexts. There is nothing that should outright cause a crash in those areas, but in effect they will produce a reset anyway, because sooner or later they will run into an invalid call stack. There is mild potential for ACE exploits here. Codes 13 and 14 point to addresses that are write-only registers of the PPU. Attempting to read those addresses will map into open bus. This means that the CPU will receive whichever value last happened to be transferred between the PPU and the CPU. My time and available tools were not sufficient to investigate the full implications of this, but it is possible that this might lead into an arbitrary code execution exploit at some point. Area code 9 loads a null pointer. In other words, the CPU will begin executing code from the beginning of the RAM. By chance, the first byte that it happens to execute is a copy of the mapper byte, which is C9, and this is an executable instruction. The next instruction is a 3-byte store instruction, at least that's what it was in my tests. And this happens to be valid as well, albeit the PPU register that it writes to ignores all writes, but the CPU happily churns along. The third instruction that it executes is BRK, causing a system reset. However, this is just what it did in my tests, and I'm not sure what sets the RAM contents from byte 1 onwards. Again, I'm sure there could be potential for ACE exploits in this, but the exact mechanism would require some extensive study. Value 11 is interesting in that it actually selects bank 3, which is Turian. By coincidence, this value works nicely. Not so fast, my dear Watson. I made a little mistake earlier. Remember that ROM bank switch code I showed earlier? I thought this code only writes 5 bits to the mapper and is done with it. Nope, that's not what happens. The register that is written here is interfaced through an address that accepts 2 bits of data at once, not just 1. While the lowest order bit is used for loading data to the relevant register, the highest order bit will reset the shift register if set. Here is what is actually happening. On areas number 8, 9, 10 and 11, the mapper shift register is reset during one or more of the bit writes, and the bank does not actually get changed. It remains as bank 0, which is used by the password codec. Area 9 is not affected by this revelation, and it still executes those same RAM bytes and ends up resetting the console. On Area 10, it now loads code from bank 0 instead of bank 4. This code runs valid but nonsensical instructions for several clock cycles, followed by one undocumented instruction, and then it issues a jump into a memory area that is mapped to a write-only PPU register. In Area 11, it now successfully calls init bank 3, but remember 2 things have changed. The mapper is not actually programmed for bank 3 now, but for bank 0, which is for Brinstar. Secondly, the mapper shift register is in a desynced state. The next time that the game wants to reprogram the mapper, it expects that the 5th write will commit the changes that it is making, but instead the very first write will do it. This will cause the game to behave in a very erratic manner, and it is only a matter of time before it crashes or resets. The game contains no mechanism to gracefully recover from this desynced state, and in fact, if you attempt this area code on the Nintendo 3DS, the console becomes unresponsive until you power cycle it, and the Virtual Console on the Wii just rage quits. I did not trace it, but I suspect that almost exactly the same thing will also happen with area code 8. Now I have been asked to explain some particular popular passwords. One of them is this Justin Bailey followed by 12 dashes. However, the fact that this password is accepted by the game is completely coincidental. In fact, I was able to craft several other short passwords that work just as well. For example, please weep gives you the Leotard Samus, but the player is expected to weep because the morph ball is gone, and the Samus does not have it, making the game unbeatable. To fix it, let's do another. Bailed me. And now the morph ball is there, and Samus is wearing her normal suit again. She bailed me. One particular popular request has been this. Engage Ridley Muffin Kicker. You thought I was going somewhere else with this? This is a well-known password that invokes the area number 11. The emulator that I am using will simply hang here, and this is because it executed the mapper switch at an inopportune time due to the shift register desynchronization, and this caused the CPU to execute a kill instruction. This is exactly the same as what would likely happen with a real console as well. However, I have a feeling that this is not the only possible outcome. Again, I would not count out the possibility for arbitrary code exploits through this area code. As a bonus, here is a list of some single-word passwords that I found. There are plenty more, but I excluded passwords that break the game. And that's all I have for this game. I am Bisqwit. Be sure to join me next time when we take a step back and cover a game that is easier to approach even by novice hackers. By the way, according to YouTube analytics, less than 6% of my subscribers have enabled notifications about my new uploads. If you like my content, make sure you click the bell icon and enable all notifications, and enable YouTube notifications as well, so you won't miss new videos. I wish you a peaceful and revitalizing day or night. See you again. Bye.